Good evening, everyone. My name is Ozochukwu and I have with me Wale Zichigo and Ilubafi Davis. We are here to make presentation on evaluation of XYZ field. In the evaluation of XYZ field, well-log interpretation and seismic interpretation was carried out across the seismic formula. In our well-log interpretation, we delineated two reservoir sands, P1 and P0.5, and these delineated reservoir sands were correlated across the world. Our seismic interpretation involved fault mapping and horizon mapping. Our fault mapping indicates that XYZ field is divided into 6 different fault blocks and that the field is bounded at the north and at the south by a fault. Then the tops of the reservoir sands were mapped across the seismic body, and these were used as an input in generating our time surface maps, which were later depth converted using polynomial velocity model. In order to find out if the mapped horizons are actually hydrocarbon bearing, we carried out seismic attribute analysis, and the results showed that away from the producing zone, which happens to be in the southeastern part of XYZ field, that additional prospects and leads exist. Our aim is to evaluate hydrocarbon potential of XYZ field for investment and development purposes. And then the objectives are seismic interpretation, generation of time and depth surface map, petrophysical evaluation, volumetries, field development and petroleum economics, lead and prospect identification, and risk assessment. These the outline that we use for this evaluation. The background information of XYZ field is that it's an offshore field located in the eastern part of the Niger Delta. This is a schematic diagram showing our workflow. For our database, we are provided with 22 wells. Out of these 22 wells, 10 wells had no logs. We are able to make use of 8 wells for our correlation. I'm going to be inviting Wale Zichigo to talk to us on the regional geology of the Niger Delta.
Alright, regional geology of the Niger Delta. The study area is located in the Niger Delta, and the Niger Delta basin is located in Niger Delta and the Gulf of Mexico on the continental Pacific margin. The basin formed as a result of the failure of the rift junction as the South American plate and the African plate separated, and as well as the expansion or the increase of the South Atlantic. So when this happened, the Niger Delta basin formed. The Niger Delta basin composes of several structural features. Part of the structural features it contains its growth faults. Now these growth faults are formed as a result of seeing deposition when deposition was going on by extensional features of the basin. The basin technically can be divided into 3 categories, which is the extensional, the transition, and as well the contraction. Of course, the contraction sits in the Akata formation, which will have some features as shade appearism. Now this shade appearism has occurred as a result of improper dewatering of the shale of the Akata formation. The Akata formation was deposited upon the first transgression, which took place in the Paleocene, of course, and then the Akata formation was deposited. After which, it wasn't allowed enough time to dewater, then the deposition of the Akata formation, which now took place in the Eocene. So this inappropriate application of time or allowance of time for it to dewater properly is responsible for the labile shale formations of the Akata formation, which results to the present shale diaparism experienced in the contraction zone, which is the Akata formation. And then growth fault, which is experienced in the Akata formation, which is technically sits on the extensional part of the basin, where extension is still resulting to high angle growth fault in the Niger Delta. So basically, the Niger Delta, our trap system is the function of these growth faults present in the Niger Delta basin. Alright. Stratigraphic framework of the Niger Delta basin. As established before, the Niger Delta basin is composed of the Akata formation at the base deposited in the Paleocene, the Abada formation deposited in the Eocene, and the current Bini formation, for which deposition is taking place till present. So the Niger Delta basin, of course, is considered a prevailing basin because the position is still taking place till today. So in the Akata formation, like I established before, we already have depositions, shale depositions, while the Abada encompasses sand deposition with parallel shales, and then the Akata, of course, sand deposition, for which deposition is still taking place till present, respectively. Using our seismic section, we're able to delineate key stratigraphic features on seismic in order to help or aid our inference or interpretation of the seismic section. So part of what we identified was the unlocking surface, which corresponds to maximum funding surface as seen in the picture, respectively, and then also the identification of top labs, which corresponds to the presence of insides valley field, respectively, using seismic. So key petroleum system elements in Niger Delta, of course, petroleum system elements involves the source rock, reservoir, the seal, migration pathways, and the trout system, respectively. As stated before, initially, I stated that the source rock, the formation that bears responsibility of the source rock in the Niger Delta is the Akata Formation, which comprises of shales where diparism occurs, and then the reservoir, of course, is the Abada Formation, and then the seal, composite of the Abada Formation, where we have paradic shales which serve as seals respectively, migration pathways, and trap system basically influenced by the growth force system in the Niger Delta. Field history, development and challenges. Of course, in the Abada Formation, several members exist. Part of the members that exist in the Biafran member, for which our reservoir sand P1 and P0.5 are members of. The sand member in the Abada Formation, for which we're looking at, is the Biafran member. The Biafran member is known basically to be prolific for hydrocarbon bearing, and it also comprises of several pressure regimes, pressure variation, which might, to an extent, compromise our integrity, respectively. Regional geology of the SYZ field. Of course, our field is located in what is known to be today's offshore Niger Delta, like I established before, on the extensional part where we have what we experience of structures as growth faults, high angle growth faults, respectively, and then our structure, growth faults, reservoir composition, clean sands, and the paradic shales, which serves as our seals, that's the Abada Formation. The position are controlled basically by faults, which divides the position into block and several depositors, respectively. Our trap system is basically, like I said, the growth fault system. Play system is structural primarily. Alright, sequence stratigraphic framework. Using the sequence stratigraphy, using our logs and then the wells we coordinated, we're able, using the Galloway method, to delineate certain surfaces, certain hints that inform on our identification and our classification of the sequence that took place in our section. Part of which is the maximum flooding surface. Using the Galloway system, we delineated the maximum flooding surface top and at the top and at the base, and then consequently identified the sequence boundaries respectively. When this was done, we used that inference using the Galloway method to delineate that upon this sequence, the first sequence boundary upward, we will be having a transgressive system tract, and then where our reservoir P1 stands for compositely, it's a high stand system tract, and then respectively a high stand system tract for our sand P0.52 respectively. Seismic stratigraphy of SYZ field. Using the seismic section again, once again, we're able to establish that a part of our seismic is chaotic, and being chaotic means that it corresponds to channel sand deposits as seen respectively. Once again, maximum flooding surfaces, developing surfaces, the size value fields, respectively using top class. Right now, we hand over to my team, Chidema to continue.
Thank you. The data that we use for our seismic to wells are sonic log, density log, and then our check shots data. Let me first mention that we are actually giving just one check shot data for where A3X. But unfortunately, where A3X happened to be one of the wells that had no logs. So by displaying our wells on map, we were able to identify the well that's closest to it, which happened to be well A8X. So where A8X, we assigned the check shot to well A8X, which we later use for our seismic to well type. First of all, we did normalization of our well logs, and then we performed sonic calibration on well A8X. After which we used it to generate, together with our density log, to generate our synthetic seismogram. To compensate for the intervals where we didn't have synthetic seismogram, we applied Gardner's equation, but unfortunately it didn't have much effect, probably because density log was missing over part of those intervals. And then to achieve our time, we made use of statistical model, making use of extraction algorithm with a time shift of -2.47. These displaying our seismic to well type, and then it shows that the tops of P1 and P0.5 fell on red reflection, while the base for the two delineated side fell on blue reflection. These are uninterpreted seismic section showing inline and crossline. This is an interpreted section showing peaked faults. As you can see from this, the XYZ field is actually marked by several synthetic and antidative faults, which is typical of the faulting system in the Niger Delta. These are faults displayed on various attributes, dividing our XYZ field into 6 different blocks, and then it shows us that XYZ field is bounded at the south and then at the north by faults. These are the various fault blocks. Therefore, our horizon mapping, the seismic to well are actually guided at horizon mapping. This is the top of sand P1, and then this is the top of sand P0.5. The horizons were mapped across the seismic volume of XYZ field, using our seismic to well type as a guide. These are horizon picking on our cross line. Then this shows the time siege that we got from the manual picking of our horizons. And this time siege map guided our picking of polygons. This map is a 2D view map showing us our fault polygons. Then with the horizon mapping, we are able to generate our time surface map. And then these time surface maps were later depth converted, making use of polynomial velocity modeling. We plotted the time and the depth values of our check shots data, and then this plot was used in generating our depth map. This is depth surface map for sand P1, and then these are depth surface map for sand P0.5. This is 2G view, and this is map view. In order to find out if the mapped horizons actually hydrocarbon bearing, we carried out seismic attribute analysis. In carrying out our seismic attribute analysis, we made use of 2 horizon time slice of envelope and sweetness attributes, and then we also made use of RMS and maximum amplitude. And then the results of these attribute analysis show that we actually have bright spots which served as our direct hydrocarbon indicators, unraveling to us the presence of possible hydrocarbon accumulation away from the producing zone, which happens to be in the southeastern part of XYZ field. These showing to us our RMS surface attributes. This is our maximum amplitude attributes. This is our envelope volume attributes. And as you can see, it's showing to us that there are actually bright spots away from the producing zone, which happens to be in block B. These are sweetness volume attributes. I'm going to be inviting Wale Zichibu to talk to us on sequence stratigraphy.
Alright, using our well logs, we're able to delineate or establish again once more a proper sequence stratigraphy for our study area. So we use 8 wells, correlated across 8 wells, and then we established again identifying maximum flooding surface using Galois method to establish key stratigraphic features that are supposed to inform for our decision, for our judgment, for where our sequence boundaries lies and all of that. So we use the Galois method again. Here is the correlation correlating across the well and all of that. Sequence stratigraphy of the study area. Using Galois method again, we establish the maximum flooding surface at the top and establish 2 another maximum flooding surface at the base. Using the Galois method, we're able to delineate appropriate sequence boundaries both for sand P1 and then sand P0.5. So using this and the stacking, and the gamma ray log, using the stacking pattern, we're able to establish using those judgments, whether it's retrograding, grading, or prograding, to delineate what what sequences influence the position of the given sound in P sound 1 and then the P0.5 sound. So we're able to establish that from here upwards, which is compositely the top boundary of our second reservoir, is a transgressive system tract, and then where our reservoir sound P1 sound fell was for the high stand system tract respectively, and then consequent to for our P0.5 sound respectively. These are thickness map for our P1 sound and then our P0.5 sound respectively. The positional models, we used basically the gamma ray log to infer the positional model for our study area. So for the P1 sound respectively, using gamma ray log, we're able to influence our judgments to what kind of environment our sand is deposited in, what kind of environment are we looking at. So basically we use the gamma ray log. As you can see, cumulatively over the whole section, it shows an a cumulative aggregate stacking pattern, so which informs our decision that we might just be dealing with the channel sand respectively. So consequently, the fluvial environment, that's for our P1 sand. Then moving to our P0.5 sand, we're able to establish a grading stacking pattern using our gamma ray log tool. So beholding the log here is showing its grading. So since it's grading, we're able to make a decision and clear judgment on what kind of environment we're looking at, and then it corresponds to a fluvial wave influenced deltaic environment respectively. At this point, I'll be handing over to Fidelis Zerba to continue.
Okay. For prospect identification, volumetrics, and risk assessment, then for our petrophysical cutoff, we used a gamma ray index to determine our maximum and minimum value, which we use to plot our net to gross value. Then we plotted volume of shell against total porosity, and this dark gray is where we have our shell, and the yellow is where we have our clean sand, while this pink is the shelly sand. Then for our petrophysics, we calculated with net to gross water saturation and porosity for each of the wells, and this is for P1 sand. Then we also did that for P. This is the summary table for P1 sand, and we also did that for P0.5. We also calculated for the net to gross water saturation and porosity for each of the wells. Then this is a summary table where we have the top, the base, the thickness, oil water contact, gas oil contact, total porosity, and the rest. Then reservoir geology. In our reservoir geology, we calculated the average net to gross porosity and water saturation for well using well A4X. Then we also did that for P0.5 sand using well A8X. Then structural cross section. This structural cross section is showing us our fluid contact for which we used our resistivity log to determine. Then this is for P0.5 cross section. Then our volumetrics. In our volumetrics, we used Petrel map based volume calculation using boundary polygon to draw our to determine our area of interest, and this particular place is our area of interest, which we highlighted there to show it clearly. Then we calculated for the total hydrocarbon in the sand for P1, and this we had to be 244 million stock tank barrel. Then for P0.5, we also calculated the total volume of hydrocarbon in P0.5, and this is the total volume we got using our average porosity, net to gross, and water saturation, and we got 390 million stock tank barrel. Then field development. Field development is actually telling us where to perforate and where not to perforate. Using our resistivity log, our neutron density, and our gamma ray log, the reds are showing us the zones of perforations, and we also know that we don't perforate close to the reservoir top so that we don't produce water. Then we don't perforate close to the hydrocarbon water contact so that we don't produce water. We are not a water producing company. Then our prospect identification. Using our root mean square, that is RMS attributes, we identified our prospect and leads. And our prospect is block A, blocks and block C. Then our lead is block F for P1 and P0.5. Then this is what we calculated using our RMS attributes. We did that for P0.5 also. Then risk analysis. In risk analysis, we did variable analysis. And using our resistivity and neutron density, we therefore recommend that nobody should develop well AX, well A8, A17, and A18 because it doesn't have neutron density and resistivity law. And in this particular one, A8, the resistivity is very flat, and that is actually water. Then risk assessment. For our source rock presence of underlying shell with efficient thickness, which may serve as promising source rock. We have a thick shell underlying the reservoir rock, which is our source rock. Then our reservoir, gamma ray is showing that we have efficient sand thickness correlated across the well with good porosity and permeability. Then our cap rock integrity, we have a good cap rock integrity. Then for our summary and conclusion, I will therefore invite Chidima Uzochukwu to conclude.
Thank you very much. In summary, field XYZ is actually a productive field with a total of 9,999 million stock tank barrel. And then we were also able to identify other leads and prospects away from the producing zone, which happens to be in the southeastern part of XYZ field. And then the limitations we had, the core data that was made available to us happened to be for well A38ZS, which unfortunately didn't have any well loss. And then we are not giving geochemistry data, and because of it, we are not able to do source rock maturity analysis. Then absence of log data for some wells. In recommendation, because the wells are actually shallow, in the long run we are expecting that we are going to be having sand production. So we are advising that enhanced recovery plan in terms of to enhance the natural drive should be put in place. Also, because we are for depths that are less than 10,000 feet, we are expecting that we are going to be having unconsolidated sands. So because of that, we are expecting sand production. Because of that as well, we are advising that sand production mechanism should be put in place. And then we are advising additional wells should be drilled in Block E to achieve optimum muzzle.